This is an example of calculating a derivative when the dependent variable is a composite function with several independent variables. Now we see here that z is a function of x and y, but x is a function of t and y is a function of t. So z ultimately depends on t, and that means that we would then be able to calculate a straight d derivative because at the end of the line there's just one independent variable. So instead of having the chain rule formula memorized for dz dt, we're going to use the custom chain rule tree diagram to develop it. The tree diagram is going to start with the dependent variable z at the top. Z depends on x and y, so our first level has two branches leading to the x and the y. X depends only on t, so there's only one branch coming down here, and y depends only on t. So here's where we can see that in the root system down here, there was only one variable t, which means that we can calculate a straight d derivative. The straight d derivatives are calculated when there's only one variable that our range element ultimately depends on, when there's only one variable down here at the root system. So let's use our tree diagram to come up with the formula that we'll use to get straight d derivative of z with respect to t. So starting at the top of the tree, we're going to need to go down both branches, but one at the time. So we'll start by going down the x branch. Now, because z depends on x and y, this first level is going to generate a partial derivative. And we'll say we're looking at the partial of z with respect to x. And then continuing down the x branch, we're going to go from x to t. And because x depends only on t, this next level is going to be a straight d derivative. So we multiply by straight d, the derivative of x with respect to t. Now to that we're going to add, we go back up to the top and we come down the y branch. Now again, this first level is a partial derivative, so this is partial z respect y, times, continuing down that y branch to t, y depends only on t, so that's a straight d derivative of y with respect to t. And this is the custom chain rule formula that we're going to use to calculate dz dt. So now we need to evaluate these partials. Partial z respect x, we look at our z function. If we're evaluating the partial with respect to x, that means we're holding y constant. This y is a constant multiple, we'll just pull that out, and then the derivative of x squared is 2x. Minus, this y is again being held constant, and the derivative of a constant is 0, so this is going to be 2xy. Now we need dx dt. Here's our x function, it depends only on t, so the derivative of x with respect to t is going to be derivative of sine is cosine. Now we need partial z respect y, so back over here to our z equation, if we are calculating the partial with respect to y, that means x is going to be constant. So this is a constant multiple of y, and the derivative of y is 1, so we just get that constant multiple x squared, minus the derivative of y squared is 2y, and so that completes this partial. Now we need dy dt, and our y variable depends only on t. The derivative of e to the t is e to the t. So now we have everything that we need to put this together using our custom chain rule. Partial z respect x was 2xy times the derivative of x with respect to t, which is cos t, plus partial z respect y, which was x squared minus 2y, times, so we'll need to put this in parens, dy dt, which is e to the t. Now the best practice is to write the answer in terms of that ultimate independent variable, which in this case is t. So let's see if we can do that without too much difficulty. Let's recall from the beginning that x is equal to sine t and y is equal to e to the t. So let's rewrite dz dt as 2 times x times y. Well, x is sine t, y is e to the t, and then all that's multiplied by cos t, plus x squared is sine squared t, minus 2y is minus 2e to the t, and then we multiply this by e to the t. And so we'll leave this as our final answer.